This is 7.2. We're still doing inverse trig functions. I know that 7.1 was a little rough. In 7.1, it focused on the graphs of inverse trig functions and really heavy on those domains and ranges, and then if they cancel each other or not. This one is going to be more how to evaluate inverse trig functions and nested inverse trig functions. So to do that, I'd like to kind of introduce what's called right triangle trigonometry. So right triangle trigonometry uses special triangles and it uses SOHCAHTOA. Right? So there are two special triangles. One is a 30, 60, 90, and the other is a 45, 45, 90. Right? And so all 30, 45, 60, and 90s, they're all the angles found on the unit circle. So instead of having to memorize all those points on the unit circle, we can use just these two triangles. Now what's special about these triangles is that the sides are always in the same ratio. Right? So a 30, 60, 90 is always going to have the sides 1, square root of 3, and 2. Now I've put them in this order on purpose because the smallest side is directly across from the smallest angle, and the larger side is directly across from the largest angle. Square root of 3 is like 1.7 or something like that, so it's the one in the middle. Right? So here I've drawn a 30, 60, 90. It's actually probably 45, 45, 90, but I'm going to label it as a 30, 60, 90. So I can label the sides according to these ratios. So the side opposite 30 degrees is going to be the smallest side. The side opposite the 60 degrees is going to be the middle length. And then the side opposite the 90-degree angle is going to be the largest side. So we're going to label 1, rad 3, and 2 always in this order. 1 is always going to go across from 30. Rad 3 is always going to go across from 60, and 2 is always going to be the hypotenuse. So I can do the same thing here with a 45, 45, 90. Right? The ratio of the sides are always in the same ratio. 1, 1, rad 2. And so if sides opposite equal angles have to be equal, so both the sides opposite the 45 degrees have to be 1, and then the hypotenuse, rad 2, or the side opposite the 90 degree is rad 2. All right, so here comes SOHCAHTOA, right? SOHCAHTOA is just an acronym to remember the ratio, right? Sine is going to be a ratio of the opposite, I don't know why I wrote adjacent here, opposite over hypotenuse. Let's fix that, okay? SOH, right? Cosine, the ratio for cosine is going to be the adjacent over the hypotenuse. And tangent is going to be the opposite over the adjacent. Now, opposite and adjacent sides are legs, right? And the hypotenuse is across from the 90-degree angle. So when we talk about adjacent to 30 degrees, we're never going to be talking about the hypotenuse. We're only going to be talking about the leg. So this is really cool. This is how we can figure out trig values. So what is sine? Actually, what is cosine of 30 degrees? Right, I'm going to look at my special triangle here. And here's my 30 degrees. So the opposite side is 1. The adjacent side is rad 3. The hypotenuse is 2. So cosine is adjacent over hypotenuse. So I'm going to find the adjacent side to 30, which is rad 3. And I'm going to put that over the hypotenuse, which is 2. So I get cosine of 30 is rad 3 over 2. What is tangent of 45 degrees? Right? Tangent, the acronym is TOA. So tangent is the opposite over adjacent. So I'm going to take one of these 45 degrees, put the opposite side over the adjacent side, and I'm going to get 1 over 1, which is just 1. Okay? All these values here for these individual trigonometric values on the unit circle can be duplicated by knowing these two special triangles. This is my preferred method, right? I don't have the unit circle memorized, but I do enjoy using these special triangles, right? So this is going to help us find those ratios. Now we can also find the reciprocal ratios. So if I wanted to know what cosecant of, let's just do 30 degrees here, right? The ratio for cosecant is the reciprocal of sine, right? So the ratio for cosecant should be the hypotenuse over the opposite, because it's just the reciprocal of opposite over hypotenuse. So I'm going to go to the 30-degree angle. I'm going to find the hypotenuse, which is 2, and put that over the opposite of 30 degrees, which is 1, and so I get a cosecant value of 2. This is really kind of slick, right? Now I'm going to use these special triangles and SOHCAHTOA in order to solve inverse trig functions, right? These are just regular trig values, right? If I wanted to do an inverse trig function, so let's do sine inverse of rad 3 over 2, okay? And so we want to know what that is. Instead of having them memorized, instead of having to go back and forth, I want you to know that inside the inverse trig function, this is the ratio, and the answer is the angle, right? This is the ratio, and the answer is the angle. So what angle has a sine ratio of rad 3 over 2? Well, what I'm going to do is I'm going to draw the triangle. And because of the domains and the restricted domains of sine, cosine, and tangent, I'm going to make sure I draw those ratios in the correct quadrant, right? So sine inverse was restricted to quadrant 1 and quadrant 4. Remember, if the ratio is positive, the angle is going to be in quadrant 1, and if the ratio is negative, the angle is going to be in quadrant 4. Now, since this ratio is positive, I'm going to go ahead and draw a special triangle in quadrant 1. Make sure that the 90-degree angle is always with the x-axis here. So the angle I'm looking for is right here, right? Now, this is the ratio for that angle. And so we have a sine inverse here. And so the ratio for sine is opposite over hypotenuse, always, right? So I know the top number is the opposite side and the bottom number is the hypotenuse. So here's the angle I'm looking for. The opposite side is rad 3. The hypotenuse is 2. So these are two sides of a right triangle. So the third number that fits this is the 1, right? We always have 1, 2, rad 3. And so the angle then is a special triangle. And the angle opposite the rad 3 is always 60 degrees. So I know this answer is 60 degrees, or in radians, pi over 3. So using these special triangles is really helpful when evaluating these inverse trig functions. So you might not have liked 7.1, but I'm really hoping that you get the hang of doing these inverse trig functions. So I'm going to do 3 more down here, just evaluating single inverse trig functions. So let's go ahead and do cosine inverse of -1/2. So since this is a cosine inverse, this is the ratio for cosine. So cosine is always adjacent over hypotenuse. So the top number is the adjacent, the bottom number is the hypotenuse. Right, now we have a negative here. The hypotenuse is never negative, FYI. It's always going to be the other, it's always going to be the adjacent or the opposite that's going to get the negative. Okay. Now, the domain of cosine inverse was 0 to pi. Cosine inverse was restricted, if you remember, to 1 or 2, right? So it was restricted to quadrant 1 if the angle was positive, and it's restricted to quadrant 2 if I'm sorry, I said angle, I meant ratio. Restricted to quadrant 1 if the ratio is positive, and restricted to quadrant 2 if the ratio is negative. So since this ratio is negative, I'm going to draw my special triangle over here in quadrant 2. Right? So here, The angle is the reference angle. We're always going to reference the angle between the x-axis and the hypotenuse there. That's what we're looking for. So I know this is the ratio for this little angle here. Right, so I'm going to label the adjacent side -1 and the hypotenuse 2. So adjacent to theta is -1 and the hypotenuse is 2. So which special triangle has a 1 and a 2? This one has a 1 and a rad 2. So it's got to be this 30, 60, 90, right? So the third side here has got to be rad 3. All right? So how many degrees is angle theta? Well, angle theta, again, is across from a rad 3. And the angle always across from the rad 3 is 60 degrees. All right? So the answer, though, is not 60. The answer is when rotated from 0. So if I were to start at 0 and rotate over to the hypotenuse, that would be 120 degrees, or 2 pi over 3 in radian measure. So make sure that the reference angle is not always the answer. It's when rotated from 0. This reference angle was the same, right? When rotated from 0 is the same as 60 degrees, the same as the reference angle. But it's not the case here for the cosine. So let's do another one. Let's do, let's go ahead and do tan inverse of -1. Okay. So now I have an inverse tangent. Here is the ratio. So if I wanted to write this as a fraction, I would put -1 over 1. Okay, and so the tangent ratio is opposite over adjacent, right? TOA. And so when I label these, the opposite is going to be -1, and the adjacent side is going to be 1. Or the negative could flip down to the bottom. That will make sense when we see this triangle. Okay, so the tangent ratio is negative. So you have to remember tangent was restricted to 1 and 4, just like sine. Okay, it was restricted to quadrant 1 if the ratio is positive. It's restricted to quadrant 4 if the ratio is negative. So again, I'm going to draw a triangle here in quadrant 4, and here's the angle I'm looking for. Right? Now this angle has this ratio. So opposite over adjacent. I'm not going to fill in the negatives just yet. I'm going to put the opposite as a 1 and the adjacent as a 1. Now down here in quadrant 4, the x is positive and the y value should be negative. So I'm going to put the negative on this vertical leg here. So if I have a 1 and a 1, what's the hypotenuse? The hypotenuse is rad 2. And this fits that special triangle, okay, the 45, 45, 90. So this angle, theta, is measured to be 45 degrees, right? But the answer isn't 45 degrees. The answer is when rotated from 0. So if we were to rotate from 0, we'd be going clockwise, which means this angle should be negative. So we would get negative 45 degrees, or negative pi over 4. All right, so let me actually just finish, just to give you 3 examples here. I'm going to finish this video so that I don't go over my 15-minute allotment and have to do this video all over again. But I have more examples coming for you in the next video.